Section 5 is about dilution of solutions. Describe the dilution of a solution, calculate the unknown concentration or volume when a solution is diluted. In a process called dilution, a solvent, usually water, is added to a solution, which increases the volume. As a result, the concentration of the solution decreases. In an everyday example, you are making a dilution when you add 3 cans of water to a can of concentrated orange juice. Look here, I've got my concentrated orange juice. This is very concentrated and it has a smaller volume. Then I add 3 cans of water. Notice my volume increases and now I have a diluted solution. But I don't just have a final volume of 3 cans of water. I have a final volume of 4 cans because I had 1 can of orange juice plus 3 cans of water. So my total volume would be 4 cans of orange juice. In a dilution, a solvent, again usually water, is added to a solution so the volume increases. The concentration of the new solution will be less than the original due to the larger volume. It would be like if I had a very concentrated Kool-Aid solution and it was so potent, I added water to it, then it makes it drinkable. In a dilution, the amount of solute does not change. I'm not adding or taking away any of the substance that makes it what it is, but I'm only changing the volume. So the grams or moles of solute in the concentrated solution is equal to the grams or moles of solute in the diluted solution. And we can use an expression called C1V1 equals C2V2, or you might see it M1V1 equals M2V2. It's the same thing. M means the molarity, and the molarity is the concentration. So C is standing for the concentration. M is also concentration. And see, it even says here, it can be molarity or percent concentration. And V is the volume of the solution. When we change the volume, there's no change in the number of particles. The solute particles just spread out because the volume of the diluted solution increases. Let's look at a sample problem. A doctor orders 1,000 milliliters of a 35% mass volume dextrose solution. If you have a 50% mass volume dextrose solution, how many milliliters would you use to prepare 1,000 milliliters of 35% mass volume dextrose solution? It tells me that I have a 50% dextrose solution. So that is my concentration that I started with, my C1. The doctor wants a 35% solution, so that's the concentration I want. And I want 1,000 milliliters of it. That's my V2. So we want to know how many milliliters would we use. We want to find V1. It depends on how you want to go. If you just want to plug everything in as is, or sometimes people want to just solve for V1. So we would divide both sides by C1 to say, okay, to find that first volume, we're going to do C2 times V2 and divide it by C1. It doesn't matter which way you go about it, you'll get the same answer. So I did 35% times 1,000 divided by 50%, and those percents will cancel out, leaving me with milliliters of solution. I want to end with 3 significant figures, so I put a decimal point after the 700, because without it, there would only be 1 significant figure. So we need 700 milliliters of our concentrated 50% dextrose solution, and we're going to put it into a new container, and we're going to fill it up to 1,000 milliliters. So we would add 300 more milliliters of water to dilute it. Let's look at this one. What is the molarity of a solution when 75 milliliters of a 4 molar KCl solution is diluted to a volume of 500 milliliters? See if you can set that one up. When we're looking at this problem, I notice that it says it's diluted to a volume of 500 milliliters. So that is my second volume. And it wants to know what is the molarity at that new volume. So we need to find M2. We're told that we have 75 milliliters of a 4 molar solution. So that is my volume and concentration of my original solution. So let's set it up. I set it up in, doesn't matter if you say C1V1 equals C2V2 or M1V1 equals M2V2, same thing. We need to find M2, so I'm going to divide both sides by 500 to get M2 by itself, and we should get 0.600, again 3 significant figures, molar diluted KCl. We started with 4 molar and we diluted it to 0.6, so that was quite a big dilution. It didn't ask us, but what if I asked you how much water was needed to dilute it? Well, I noticed that my original concentration at 4 molar had a volume of 75 milliliters. So I was at 75 milliliters and I diluted it up to 500 milliliters. I didn't add 500 milliliters of water. That's my final volume after diluting. So I can just subtract it. So I added 425 milliliters of water to dilute it. Take a minute to look over the learning goal for this section. Section 6 is about chemical reactions in solution. The learning goal is that given the volume and concentration of a solution in a chemical reaction, you can calculate the amount of a reactant or product in the reaction. When chemical reactions involve aqueous solutions, we use the balanced chemical equation, the molarity, and the volume to determine the moles or the grams of a reactant or product. Let's look. Zinc reacts with hydrochloric acid to produce hydrogen gas and zinc chloride. Here's our expression, and it's balanced. How many liters of a 1.5 molar HCl solution will react completely with 5.32 grams of zinc? We are given molarity of hydrochloric acid, and we're given grams of zinc. So we need to hop from one substance to the other. We're going to start with, the first thing I notice, grams of zinc. Anytime we're given grams of something, we need to get to moles of it. So let's look at the periodic table and figure out the molar mass of zinc. Step 1, I went from grams of zinc to moles of zinc using the molar mass. So I got 0.08133 moles of zinc. All right, now we need to look at how to get from moles of zinc to moles of HCl. And notice that for every 1 mole of zinc, there's 2 moles of HCl. That can give us our mole ratios. Now, which one do we want to use? If I've got moles of zinc, I need to get rid of moles of zinc, so I need moles of zinc on the bottom. 1 mole of zinc on the bottom for every 2 moles of HCl, and that will give me, when those cancel out, 0.1627 moles of HCl. Well, I'm not quite done yet because it wants liters of HCl. I'm given, though, that it's 1.50, capital M means that that's how many moles of HCl there is for 1 liter of HCl. So this can become another conversion factor. I can say that there's 1.50 moles of HCl in 1 liter, or I can say in 1 liter of HCl, there are 1.50 moles of HCl. Which one do you think we will want to use since I have 0.1627 moles of HCl? Remember, I want liters and I've got moles. So we want to use the expression to get rid of the moles of HCl. Therefore, we would use this conversion factor. We would say 1 liter of HCl for 1.50 moles of HCl. And notice that by doing that, the moles of HCl will cancel, leaving me with liters of HCl. That's what I'm trying to get to. And I got 0.10844 liters of HCl. Let's go back and look at our problem to see how many significant figures we want to end with. We started with 3 sig figs here and 3 sig figs here. So let's finish with 3 sig figs. 0.108 liters of HCl solution would be needed. And again, we did this all by having a balanced equation. I started with grams of zinc, I went to moles of zinc, and I was able to hop from moles of zinc to moles of HCl. We did that using stoichiometry, but now we're able to see that we can do that with solutions as well. Let's work through this problem. How many milliliters of a 0.250 molar barium chloride solution are needed to react with 0.0325 liters of a 0.160 molar sodium sulfate solution, given this balanced equation? Let's look at what we know. We have a volume and a concentration of sodium sulfate. If I know sodium sulfate's concentration, that means that I know that I have 0.160 moles per liter of Na2SO4. And I'm told that I have 0.0325 liters of it. Well, let's multiply this concentration by that 0.0325 liters of Na2SO4, because liters and liters will cancel out. leaving me with moles of Na2SO4. Now that I have moles of Na2SO4, I can hop from Na2SO4 to barium chloride. Notice it's a 1-to-1 ratio. So 1 mole of Na2SO4 to 1 mole of barium chloride. That will cancel out my moles of Na2SO4, leave me with just 0.0052 moles of barium chloride. Also, I know the concentration of barium chloride, that it's 0.250 moles of barium chloride for a liter of barium chloride. I have moles of barium chloride. How would I use this conversion factor to get rid of my moles of barium chloride and get 2 liters? Well, I would need to flip-flop that around, right? I'm going to say 0.0052. I'm going to leave off my units just because I don't have room for it. But that is moles of barium chloride. So I need my moles of barium chloride on the bottom. The 0.250 moles of BaCl2. Those will cancel for 1 liter of barium chloride. And that gives me 0.0208 liters of barium chloride. Cool, we're done. Oh, almost. It wants milliliters. This is in liters. So let's just times it by 1,000. 1, 2, 3. That would be 20.8 milliliters of barium chloride. Again, what did we do? We were given volume and concentration of one substance. And because I know volume and concentration, I can find moles of that substance. And if I know moles of something, I can go from moles of one thing to moles of another thing. So that led me to moles of barium chloride. And I was given concentration of barium chloride. So I was able to go from moles and cancel out moles to get to liters. And then just multiply by 1,000 to get to milliliters. And this is it set up all in one piece, but we did it piece by piece. We did this first, and then we did our mole to mole ratio, and then we did times the concentration when we flip-flopped that conversion factor, and then we multiplied it by 1,000. And again, it should be 20.8 milliliters of barium chloride. Let's look at another sample problem. We're told that acid rain results from the reaction of nitrogen dioxide with water. Here's our balanced equation. At STP, how many liters of NO2 gas, so we want to find liters of gas, are required to produce this many liters of 0.4 molar HNO3 solution? Remember, let's write this out. 0.400. This means moles of HNO3 per liter of HNO3. And I know that I have 0.275 liters of HNO3. So if I know liters of HNO3 and moles per liter of HNO3, let's get rid of, since I have 2 liter units, let's get rid of liters and leave me with just moles of HNO3. And because liters is on the bottom here, I can just multiply by 0.275 liters of HNO3, and that'll cancel liters and liters, leaving me with moles. If I know moles, I can get to moles of another substance. That left me with 0.11 moles of HNO3. Let's bring that up to the top here. 0.11 moles of HNO3. Once I have moles of something, I can hop from HNO3 to, we want NO2 over here. So I would say that there's, for every 2 moles of HNO3, there are 3 moles of NO2. Let's see what that is. And that gave me 0.165 moles of nitrogen dioxide. Now at standard temperature and pressure, we know that any gas, for 1 mole of gas, there is 22.4 liters of it. So I'm going to write that conversion factor. So for 1 mole of NO2, there's 22.4 liters of NO2. And again, we could write this 22.4 liters on top for 1 mole of NO2 on the bottom. How would we need to write that to get liters? Well, if I've got moles right here, I would need to have my 1 mole on the bottom and the 22.4 liters on top. And that will cancel out my moles of NO2, leaving me with liters of NO2. So what is 0.165 times 22.4? That would give me 3.696. And I will have 3 sig figs here and 3 sig figs here. So let's go 1, 2, 3. That 6 will round that 9 up. So 3.70 liters of NO2. Let's walk through our step process. I went from liters of solution to moles of solution. Liters and liters canceled out to moles of the HNO3. And then I went moles of HNO3 to moles of NO2. And for every 1 mole of any gas at STP, there's 22.4 liters. If I cancel everything out diagonally, that leaves me with liters of NO2. Take a look at the summary of pathways. It's also in your notes, as well as the review looking at the learning goals from this section.